In our digital world, we're always trying to make things smaller, faster, and just more efficient. Think about it: zipping files, streaming videos. Data compression is the unsung hero behind so much of what we do. But what happens when you have to compress data with a really specific, really tough constraint? Well, today, we're cracking a coding challenge that's all about that. And here it is. This is the heart of the puzzle. See, it's one thing to shrink data by just creating a brand new, smaller copy. But it's a completely different ballgame to shrink it within its own footprint, modifying it on the fly. And that's the riddle we're going to solve today. So here's our game plan. We'll start with the basic compression challenge. What are we even trying to do? Then we'll dig into the in-place twist that makes it so tricky. After that, we'll uncover the awesome two-pointer solution, walk through a real example step by step, and then wrap it all up with the key takeaways. All right, first things first, let's get a super clear picture of what this algorithm is actually supposed to do. What's the end goal here? Okay, so the basic idea is something called run-length encoding. It's a classic. We're going to scan an array for groups of identical characters that are all right next to each other. Like a bunch of A's in a row or a couple of B's. Once we find a group, our job is to replace it with something way more compact, just the character and how many it appeared. The rules are actually pretty straightforward. As we're looking through the data, if we find a character that's all by itself, a group of one, we just keep that character as is, no change. But if we find a group of repeating characters, say CCC, we replace that whole sequence with just two things: the character C and its count, the number 3. Simple enough, right?
And here you can see it in action. Look at the before array. The two A's, they become A2. The two B's become B2. And those three C's become C3. And just like that, you can see the resulting array is shorter than what we started with. That's a win.
Now, here's where it gets a little more interesting. What happens if a character repeats like 10 or more times? So say we have 12 B's. We don't write B and then the number 12. No way. The algorithm is smarter than that. It splits the number into individual digits, so it becomes B followed by the character 1 and then the character 2. This is a super important detail to remember for the logic. Okay, so all of that seems pretty manageable, right? Scan, count, replace. But now we get to the constraint. The one rule that turns this from a simple task into a real brain bender. There it is. That's the catch. We're not allowed to build a nice, clean new array to put our answer in. We have to do this whole compression operation directly inside the original array. We're essentially overwriting the data as we process it. This is just the technical, nerdy way of saying no new arrays. You can have a few variables to keep track of counts and positions, sure, but you can't create a whole new data structure to build your answer. You've got the one array you were given, and that is it. I mean, think about it. The easy way would be to just read the input, build up a brand new compressed string on the side, and then copy it back at the end. But we can't do that. The required method is more like performing surgery. You have to carefully read from one part of your patient, the array, while you're simultaneously writing into an earlier part, all without messing up the data you haven't even looked at yet. So how on earth do you solve a puzzle like that? How do you modify an array while you're still reading from it? Well, the answer is a really elegant and powerful technique that, once you see it, you'll see it everywhere. We use two markers, or pointers. One pointer's entire job is to run ahead and read the data, figuring out where the groups of characters begin and end. The other pointer kind of hangs back, and its job is to write the compressed results back into the front of that same array. Yeah, let's give them some better names to make this crystal clear. Let's call the read pointer our scout. It's the one that runs ahead, exploring the territory, counting how many A's or B's it finds in a row. And the write pointer? That's our builder. It stays put, back at the start of the array, just waiting for reports from the scout. As soon as the scout radios back, hey, I found 3 C's, the builder gets to work and carefully writes C and then 3 into the array. Okay, I know this might sound a bit abstract, so let's make it super concrete. We're going to trace our scout and our builder through that first example and see exactly how this dance works. All right, here's our starting line. We've got our array, both our scout, which we'll call I, and our builder, which we'll call K, are starting right at the very beginning, index 0. Everyone's ready to go. Okay, first move. Our scout I takes off. It sees an A. It moves to the next spot, sees another A. Then it sees a B. Aha, the group of A's is over. So the scout reports back, found a group of 2 A's. Now our builder K, who's been waiting at the start, gets to work. It writes the character A right where it is at index 0, and then writes the count 2 at the next spot, index 1. The builder has now moved up and is waiting at index 2 for its next job.
And the process just repeats. The scout picks up right where the last group ended at the first B. It finds 2 Bs and then hits the Cs. It reports back again. Our builder K, patiently waiting at index 2, writes the character B and then the count 2. The builder now moves forward to index 4. You see the pattern?
And for the final group, the scout picks up at the first C, scans all the way to the end, and finds a group of 3. The builder, waiting at index 4, writes C and then 3. It now comes to rest at index 6. And check it out, the entire compressed result, A2, B2, C3, is now sitting perfectly in the first 6 spots of our original array. And that leftover C at the very end, it's still there technically, but it doesn't matter, because we know our new compressed length is only 6. And that's the final piece of the puzzle. The final position of our builder pointer K is the answer. That number tells us the new length of our compressed array. So in this case, it's 6. The function returns that number, and boom, problem solved. Look, this isn't just some clever trick for one random problem. The pattern we just saw is incredibly useful. So let's just take a second to recap the big ideas here.
So what are the core concepts you should really take away from this? First, the real challenge was never just about compressing the string. It was about doing it in place without any extra memory. Second, that 2-pointer technique, our scout and builder, is the perfect solution for this kind of problem. It gives us a clean way to separate the active reading from the active writing. And finally, remember that our builder pointer does double duty. It doesn't just write the new data, its final location literally gives us the answer, the new length of our array.
And I think this quote just sums it up perfectly. We took what looked like a problem about memory constraints, about not having enough space, and we turned it into a problem of choreography. It's all about making sure our scout and our builder can dance together in perfect sync without ever stepping on each other's toes. And that leaves us with one final thought to chew on. This powerful scout and builder pattern, it shows up in a ton of other problems. Things like removing duplicates from a sorted array or moving all the zeros in an array to the end. So the next time you're faced with a problem that tells you to modify an array in place, just ask yourself, could this just be another pointer coordination